Today we are going to discuss multiplexers. See, here this is a multiplexer, and what the multiplexer does is, if you have a set of inputs, say I0, I1, etc. up to In minus, that means n inputs are there, and from this input you are going to select one output. That means one among these inputs are directed to the output. Okay, that means all others are neglected. And here we have a set of selectors, and depending on the values of these selectors, one of these inputs is redirected to the output. That means this is a multiplexer. That means here we have n to 1 multiplexer, means you have n inputs, and from this n inputs, one of this is selected and that is directed to the output depending on the set of selectors. For example, here we have this as selector. It steers one of the many inputs to an output. That means you have a set of inputs, and from this set of inputs you are going to select one among this and you are directing that to the output. Okay, and that is depending on the selection criteria. These are selectors that we will discuss. Select one input from many based on control signals. These are the control signals of selectors, and depending on the values of these selectors or control signals, one of this is selected and that is bypassed to the output. Number of selectors and number of inputs. Here we have how many inputs? Here we have n inputs and one output. N inputs and one output. That is why we call it as n to 1 multiplexer. For example, suppose that you have a 2 to 1 multiplexer. See, here you have two inputs. These are two inputs, A and B, and one of this is selected. So here how many inputs are there? Two inputs are there. For selecting, so here this selection, suppose that this is the selector S. Here this is having only one bit. S is one bit. Why? Here when S is equal to 0, suppose that you are going to bypass or you are going to select this A to the output. And if S is equal to 1, you are going to select this B to the output. That means if you have only two inputs, you need only a single bit for the selector, or that can act as the control signal. And suppose that you are having four inputs, A, B, C and D. Suppose that you have four inputs, A, B, C and D. Now, using only a single bit, you cannot select these four. That means for selecting this four, you need at least 2 bits. 2 bits are needed for selecting this. Okay, that means when this selector is 0, 0, you are going to select A. When it is 0, 1, you are going to select B. When it is 1, 0, you are going to select C, and when it is 1, 1, you are going to select D. That means this is an example of a 4 to 1 multiplexer. For that you need 2 bits. Instead of a single bit, you need 2 bits for this selector. That means if the selector is, this is selector. If selector is 0, 0, you are going to select A. If the selector is 0, 1, you are going to select B. And if it is 1, 0, you are going to select C. And if it is 1, 1, you are going to select D. That means to have a 4 to 1 multiplexer, you need 2 bits or 2 bits selector. You need a 2 bit selector. Likewise, if you have 8 to 1 multiplexer, from 8 inputs you are going to select 1 outputs, you need 3 bits for the control signals or selector signals. If it is a 16 to 1 multiplexer, from 16 input symbols you are going to select 1 output, then you need 4 control signals or 4 bit selectors. Likewise, here if you are having n inputs and from these inputs you are going to select one output, you should have S0 S1, or you should have log n to the base 2 number of bits. Log n to the base 2. For example, log n to the base 2. This much number of selectors are needed. If n is equal to 2, if it is a 2 to 1 multiplexer, this is 1. 2 to 1. If it is log 2 to the base 2 is 1. That means if you have 2 inputs and 1 output, you need 1 bit selector. If it is n is equal to 4, what will happen? 4 to the base 2 is, this is 4 is 2 square, and that means 2 log 2 to the base 2, that means this is 2. That means log 4 to the base 2 is 2. That means if you have 4 inputs and 1 output, you need a 2-bit selector. If it is 2 cube, that means if it is an 8 to 1 multiplexer, you need 3 bits. If you have 2 raised to 4, that means if you have 16 to 1 multiplexer, you need 4 bits for control signals. Likewise, if you have n bits, you need n to the base, log n to the base 2. Okay, and that's all about multiplexers in general. Now, this is just like a telephone exchange, and this is one application of a telephone exchange. That means, suppose that you have a single line. Suppose that if you have a single line, in our earlier telephone exchanges, we had only a single line, and suppose that 4 subscribers want to have a telephone call, and suppose that you have a single line, one of the subscribers has to be selected, and that depending on some selector, you are going to select that subscriber. That means 4 subscribers are going to use, or they want to use the same channel at the same time, but only one of them can be allocated, and for that you have, that means these are the subscribers, and one of these subscribers has to be selected for making the call, and that is depending on selectors. That is one application. And here this is another application. That means if then else equivalent to 2 to 1 multiple. That means if you have 2 inputs A, B and C, that means if your inputs are B and C, and depending on the value of A, here if A equal to 0, then Y equal to C, else Y is equal to B. That means if you have 2 inputs B and C, and this is the output Y, and if A equal to 0, Y is equal to us, B is assigned equal to B, else Y is assigned equal to C. That means you have 2 inputs B and C, and one of this is assigned to Y. That means this Y is selected either as B or C, depending on the value of A. Depending on the value of A. If A is equal to 0, what will happen? Y is equal to C. That means Y is assigned equal to C. And if A is equal to 1, else means if A is equal to 1, Y is assigned to B. That means this is the truth table for that. That means you have 3 variables. That means actually we have 3 inputs A, B and C. A is the selector, and depending on the value of A, you are going to bypass this, or you are going to assign this Y to either B or C. Okay, that means depending on the value of A, B and C, depending on the value of A, B and C, if A is equal to 0, if A equal to 0, then Y is equal to C. If A equal to 0, then Y is assigned equal to C, and else if A is equal to 1, then Y is assigned equal to B. See, here for this 4 variables, this is A equal to 0 and this is A equal to 1. Okay. If A equal to 0, what will happen? Y assigned equal to C means here the value of C is assigned to, that means 0 to 0, 1 to 1, 0 to 0 and 1 to 1. That means C is copied to Y. C is copied to Y. And if A is equal to 1, what will happen? Y is assigned to B. That means B is copied to Y. That means 0 to 0, 0 to 0, 1 to 1, 1 to 1. Okay. That means this is the truth table. That means depending on the value of A, B and C, the value of y is assigned. And using Karnaugh map and your simplification techniques we already studied, can have an expression for y, can straight away write that. That means if A equal to 0, then A dash will be 1. If A equal to 0, A dash will be 1. And A dash C means if A equal to 0, what will happen? A equal to 0, A dash will be 1 and A dash will be 1. If A equal to 0, A dash will be 1 and 1 into C plus what is 0? If A equal to 0, 0 into B. That means if A equal to 0, A dash will be 1, that 1 into C plus A is 0, 0 into B, which is C. That means if A equal to 0, y equal to C. And suppose that A is equal to 1. In that case, A dash should be 0. That means 0. A dash should be 0 into C plus A is equal to 1 into B. That means 0 into C is 0 plus 1 into B, which is B. That means this is the simplified expression for this y. And that is implemented here. That means you are going to generate AB here. A into B. This is an AND gate. This is AB and this is A is complemented. Here it is A dash and A dash into C. This is A dash C and this is, we are ANDing these two. That means AB plus A dash C. AB plus A dash C. This is the expression, or this is the combination circuit implementation of a 2-to-1 multiplexer. This is the implementation of 2-to-1 multiplexer, and depending and I am going to have the equivalent representation. That means this is a 2-to-1 multiplexer. Here we are going to have B and C here and A here and Y is the output. So actually this is this is the implementation of this. That means the circuit inside is this one. This is the this is the circuit inside. This is the circuit inside, and that's given here. That means 2-to-1 multiplexer, and this is the implementation of a 4-to-1 mux, or mux is simply multiplexer, 4-to-1 multiplexer. Here for this 4-to-1 multiplexer we have 4 inputs. 4 inputs I0, I1, I2 and I3. 4 inputs are there, and number of selectors will log 4 to the base 2. That means we have 2 selectors or control signals are there, and those control signals are S0 and S1. Can simply given here instead of S0 and this is S1 and this is S0, and depending on the value of S1 and S0, if S1 and S0 are 0, 0, this I0 is selected. If it is 0, 1, I1 is selected. If it is 1, 0, I2 is selected, and if it is 1, 1, I3 is selected. That means this is the truth table. If S1, these are the values of S1 and S0. That means depending on the control signals or depending on the selectors, you are going to select this Y. That means if S1 is equal to 0 and S0 is equal to 0, that means if both of these are zeros, then S1 dash and S0 dash will be S1 dash and S0 dash will be 1. That is why we have S0 dash, S1 dash, I0. That means if and all others will be 0. That means once you have this S0 dash and S1 dash is equal to 1, then I0 will be selected. And S1 dash and S0, that means 0, 1. That means if S1 is 0 and S0 is 1, that means if S1 is 0, then S1 dash will be 1. That means this term will be, if S1 and S0 are 0 and 1, this term is non-zero and all others will be zeros. If it is S1 and S0 1, 0, that means S1 S0 dash. That means when S0 is 0, S0 dash will be 1 and this term will be selected. And if both of them are 1s, S1 and S0 I think. That means if this is the sum of products form and this is the sum of products form for the 4-to-1 multiplexer, and this is the implementation of that. You can study this your own, because this is self-explanatory. That means here you are going to have, say here this is 0 0. That means this is S1 dash S0 dash, what is this, I0, and this is what, this is S1 0 0. This is S1 dash and S0 dash. That means this is S1 and this is S1 dash. This is S0, this is S0 dash, and this is S0 dash, S1 dash, S0 dash, I0. This is S1 dash, S0, I1. What about this? This is S1, S0 dash, I2, and this is what? S1, S0, I3. That means you are going to sum those and you will get Y. And this is the circuit inside this 4-to-1 multiplexer. This is a 4-to-1 mux. And that is about the implement. That means here you have how many inputs? Actually we have 1, 2, 3, 4, 5, 6. 6 inputs are there. Here see 1, 2, 3, 4, 5 and 6. These are the inputs. Input to this mux and only a single output, and this is the single output. 4-to-1 mux from 2-to-1. That means using 2-to-1 multiplexer, how 4-to-1 multiplexers can be implemented. For a 2-to-1 multiplexer, we have two inputs. That means here you have, say, I0 and I1. These are the inputs, and depending on a single S0, you are going to have a Y. That means depending on the value of this S0, you are either selecting I0 or I1. That means this Y is equal to S0 S0 dash I0 plus S0 I1. That means if S0 is equal to 0, S0 is equal to 0, what means that means this term is 0 and this S0 dash will be 1 into I0. That means this I0 will be passed to Y. And if S0 is equal to 1, what will happen? S0 dash will be 0 and this term is 0, and S0, this 1 into I1, that means I1 will be bypassed. That means this Y1 or I1 will be available at Y. That means we have S0 dash I0 plus S0 I1. Likewise, here see, here this is the expression for a 4-input mux, 4-to-1 multiplexer. This is, you have inputs I0, I1, I2 and I3. 4 inputs are there, and you have two control signals which are S1 and S0, and this is the output Y. And in our earlier discussion we have proved this. That means Y is equal to S1 dash S0 dash I0 and S1 dash S0 I1 plus S1 S0 dash I2 and S1 S0 I3. That means depending on the value of S0 and S1, either of these 4 will be 1. All others will be 0. That means depending on the value of S0 and S1, 4 among these products, one of this is 1, on all of those will be 0. That means that term into either I0, I1, I2 or I3, that term has to be bypassed to the output. Okay. That means here how many inputs are there? I0, I1, I2 and I3. And we have two control inputs S0, S1 and S0, and depending on the value of S1 and S0, one of this will be available as Y. Okay. Now, this is the expression for that. And now we are going to discuss how this can be achieved using 2 or 3 a 2 to 1 multiplexer. Suppose that you have a chip available for a 2 to 1 multiplexer, and suppose that you are in need of a 4 to 1 multiplexer. So how to implement that using 2 to 1 multiplexers? That is the point of discussion here. Now I am going to group this, that means S1 dash, that means the S1 dash is common for these two, that means I am going to take that out, S1 dash into S0 dash I0, what remains here, and S0 I1 remains here, that means S1 dash into S0 I, this plus. Now S1 is the common factor for these two, then S1 into this. Okay. Now I am going to rename this product as, this sum of product as Y1 and this sum of product as Y2, and this is S1 dash Y1 plus S1 Y2. That means this is actually this S1 dash Y1 plus S1 Y2. If you have a multiplexer and suppose that you have two inputs, say Y1 and Y2. Suppose that you have two inputs Y1 and Y2, and suppose that it is controlled by S1, and S1, depending on S1, if it is S1, if S1 is true, then Y2 will be bypassed, and if S1 is equal to 0, Y1 will be bypassed. Since this is a 2 to 1 mux, this is a 2 to 1 mux. That means this is the output Y. That means if we have two inputs Y1 and Y2, depending on the value of this S1, one of that will be available as the output. Then what is Y1 and Y2? Y1 is S0 dash I0 plus S0 I1. That means that is another 2 to 1 multiplexer. Here the inputs are I0 and I1, and depending on the value of this S0, either I0 or I1 will be available as Y1. That means here the output of this is Y1, this is the output Y1, and that will be generated by a multiplexer in which the control input is S0. The control input is S0 and the inputs are I0 and I1. Here you have two inputs I0 and I1 as the inputs. You have two inputs I0 and I1, and depending on the value of S0, one of these I0 or I1 will be selected, and that is Y1. And now we are going to have another Y2. Y2 is S0 dash I2 plus S0 I3. That means in that case, again you have two inputs S0 and S0 dash and S0. That means here the control input is S0, and we have two inputs I2 and I3, and depending on the value of I2 and I3, depending on the value of I2 and I3, or sorry, depending on the value of S0, either I2 or I3 will be selected. If S0 is equal to 1, I3 is selected, and if S0 is 0, I2 will be selected, and that is Y2. And I am going to give Y2 here and Y1 here. That means here again, here you have a 2 to 1 multiplexer. That means here you have 3 2 to 1 multiplexers. It is a mux tree. That means this is like a tree. That means this is the root and these are the leaves. And you can have a mux tree. Here in this case, here S0 is given as inputs to these two muxes, and here S1 is providing here. That is another mux, and this is the implementation of. This is how a 4 to 1 multiplexer is implemented using 3 2 to 1. Now we are going to implement an 8 to 1 mux using 4 to 1 and 2 to 1 multiplexers. That means here we are going to have two 4 to 1 multiplexers and a single 2 to 1 multiplexer. We are going to have, see here, this is an 8 to 1 multiplexer. Here we have This is 8 to 1 mux, and here you have 8 inputs, and depending on the value of S2, S1 and S0, if 3 of them are zeros, I0 is selected. If it is 0, 0, 1, I1 will be selected, and if it is I2, 0, 1, 0 is selected, and like that. That means depending on S2, S1 and S0, you can have a single 8 to 1 multiplexer. But if you have 2 4-to-1 multiplexers and 1 2-to-1 multiplexer, you can easily implement this using a mux tree. For example, here you are going to provide S1 and S0 here, S1 and S0 here. If S1 and S0 are zeros, here it is 0, 0, here it is 0, 0. That means here you are going to provide 4 inputs to this mux, and S1 and S0 as its control signals. And here for the second mux, you are going to provide I4, I5, I6 and I7 are inputs, and again S1 and S0 are the control signals. Suppose that S1 and S0 are zeros, what will happen? If S1 and S0 are zeros, S1 and S0 are 0 for this and in this. That means for this group, this is the first group and this is the second group. This is the first mux and this is the second mux. From the first mux, if S1 and S0 are 0 and 0, what will happen? I0 is selected. I0 is selected, and from this group, I4, I5, I6 and I7, if S1 and S2 are 0, zeros, what will happen? I4 is selected. I4 is selected. See, from this group, I0 is selected. That means from this group, I0 is selected, and from this group, I4 is selected. This is I4, and now if you see the value of S2, S2 is 0 for I0 and S2 is 1 for I4. That means depending on the value of S2, either I0 or I4 is selected. That means I4 or I0 is selected depending on the value of this S2. This S2. Another case, say, suppose that you are going to have this I6. You have to select I6, and in that case the value of the control signals S2, S1 and S0 will be 1, 1, 0. Then what will happen? This is 1, 1, 0, and in that case S1, S0 will be 1, 0. S0, S1 will be 1, 0. That means this is 1, 0 and this is 1, 0. When these two are 1 and 0, what will happen? From this first group, S1, S2 is 1, 0 for this, and for this group 1, 0 is for this. Okay, that means from this group I2 is selected. I2 is selected, and from this group what will happen? I6 is selected. I6 is selected. I2 and I6 are selected, and depending on the value of S2, here S2 is 1. What will happen? S2 is 1. In that case, I6 is selected. That means Y is equal to I6 in this case. In that way, you can have an implementation of an 8 to 1 multiplexer using 2 4-to-1 multiplexers and a single 2-to-1 multiplexer. Okay. Now suppose that if they are asking, suppose that you have only 4-to-1 multiplexers, you don't have any 2-to-1 multiplexers. In that case, here you can have 4-to-1 multiplexers also. 4-to-1 multiplexer. So in that case, you need 2 inputs. That means here you have to short those 2, and here we are going to provide 0. That means the input will be either 0, 0 or 1, 1. That means this S2 will be either 0, 0 or 1, 1. In that case, you are going to provide 0, 0. That means here you have 4 inputs to this, and here for 0, 0 input you are going to provide this I2 or Y1, and for 1, 1 input you are going to provide this Y2, and you have to make the other 2 inputs. That means 4 inputs are there. You have to provide this I2 through I2 as the first input, and you have to provide this Y1 as the first input and Y2 as the last input, and you have to make that means these two can be ignored. There is no significance. That means if S2 is 0, then this will become 0, 0, and this will be selected. Y1 is selected, and if it is 1, Y2 is selected. In that way, you can implement an 8-tone multiplexer using only 4-tone muxes. You can have the implementation of 8-tone multiplexers using only 2-tone multiplexers. In that case, what will happen? You have to provide, that means every 4-tone multiplexers has to be implemented using 2-tone multiplexers. And in that way, you can have any kind of mux trees. And it is up to you to have a detailed study about the mux trees. And using these mux trees, you can implement, or suppose that chips are available for a 4-tone only, then suppose that if you want to have a 16-tone multiplexer, then how to implement that using only 4-tone multiplexers. And that's up to you to have a detailed study about. This is a problem, that means this is a question, and implement the following Boolean function using mux. That means this is sum of products form. That means f of x, y, z is equal to sigma 1, 2, 6, 7 means here you have 3 inputs, and for 1 that means 0, 0, 1, and 2, 0, 1, 0, for 6, 1, 1, 0, and for 7, 1, 1, 1, you have to set this function as 1. For all others, you have to set it as 0. Now, I am going to have a mux, and here anyway you have 3 inputs x, y, and z, and you have to generate f of x, y, z. That means output is definitely f of x, y, z. This is f of x, y, z. And now suppose that you are going to use a 4-tone multiplexer, 4-to-1 mux. 4-tone mux, definitely you have 2 inputs. Suppose that your inputs are x and y. Suppose that your inputs are x and y. This is x and this is y. And you have 4 inputs here. And suppose that is various forms of z. And say, if x and y are 0 and 0, this is x and y 0, 0. This is x and y 0, 1. This is x and y 1, 0, and this is 1, 1. Okay. When x and y are 0 and 0, what will happen? Z is f of x, y, z is equal to z. That means when x and y are 0 and 0, what will happen? Here z is 0, f of x, y, z is 0. Z is 1, f of x, y, z is 1. That means when x and y are 0 and 0, this z is bypassed. That means actually when x and y are 0 and 0, and now you have I0, I1, I2, and I3, then if x and y are 0 and 0, you have to bypass this I0 to the output. Okay, I0 to the output. But here when x and y are 0 and 0, here z is bypassed. That means f of x, y, z is equal to, here it is 0, here it is 0, here it is 1, here it is 1. That means that z is bypassed. So I am going to provide this instead of 0, here you are going to provide z. Now see, x and y are 0 and 1. then this I1 is selected. When x and y are 0 and 1, this I1 will be selected. See, when z is 0, this f is 1, and when z is 1, f is 0. That means actually you are going to count. That means when x and y are 0, 1, x and y are 0, 1, what will happen? You have to complement this. That means the complement form of z is the output. That means when x and y are 0 and 1, what will happen? If z is here, then that will be z dash. Then here it is z dash will be the output. Then here z dash will be the output. Z dash. Okay. That means output will be z dash. Then if it is 1 0, what will happen? If it is 1 0, all outputs are zeros. That means here, regardless of whether it is 0 or 1 here, the output will be 0. That means I am going to replace this by 0. Now I am going to have 1 1 here. 1 1 here, what will happen? 1 1. That means if both are 1s, regardless of whether this is 0 or 1, the output will be 1. That means here it is 1. That means this is the implementation of f of xyz using 4 to 1 multiplexer. With that, I am concluding the session on multiplexers. Thank you.